Carbon buildup is destroying Subaru engines, slowly, invisibly, expensively, on direct injection. Subarus, which is every current model and most models built since 2011, carbon deposits accumulate on intake valves, piston crowns, and combustion chamber surfaces with every single mile you drive. There is no way to completely prevent it. The direct injection design physically prevents fuel from washing the intake valves clean, the way older port-injected engines did automatically. The standard solution: professional walnut shell blasting. The shop removes your intake manifold, blasts crushed walnut shells through the intake ports at high pressure, and cleans the carbon deposits off the valve faces. Cost: $600 to $1,200 depending on your model and local labor rates. Recommended interval: every 40,000 to 60,000 miles on heavily affected engines. Over the life of a 300,000-mile Subaru, that's potentially $3,600 to $7,200 in carbon cleaning services. But there's a $0 trick that dramatically slows carbon accumulation, delays the need for professional cleaning, and in some cases removes existing light deposits without any professional service whatsoever. $0. No parts, no chemicals, no tools. Just a specific driving technique that uses your engine's own combustion process to burn off carbon deposits before they accumulate to the point of causing problems. I've seen this technique extend the professional cleaning interval from 40,000 miles to 80,000 miles on the same engine. I've seen it eliminate rough idle symptoms on engines with moderate carbon accumulation. I've seen it improve fuel economy on vehicles that had been gradually losing efficiency to building deposits, all for free. Today I'm explaining exactly what this technique is, the science behind why it works, how to implement it correctly, and what to combine it with for maximum effectiveness. Let's get into it. Understanding carbon buildup, why it happens. Before the technique, understand the problem at a fundamental level. This understanding tells you exactly why the $0 trick works. The direct injection problem. In older port-injected engines, fuel sprayed directly onto the back of the intake valve on every intake stroke. The fuel acted as a solvent, continuously washing deposits off the valve face. This is why port-injected engines rarely develop significant intake valve carbon problems. Direct injection engines spray fuel straight into the cylinder, completely bypassing the intake valve. The intake valve sees only air and whatever oil vapor comes through the PCV system. No fuel, no washing, no natural cleaning mechanism. The oil vapor from the PCV system is the deposit source. This vapor enters the intake manifold, coats the intake valves, and bakes onto the valve surface as hard carbon deposits with every heat cycle. Every drive, every mile, deposits accumulate. What carbon deposits actually do? Carbon deposits on intake valves restrict airflow through the intake port, reducing the air volume entering the cylinder. They disrupt the airflow pattern that promotes complete combustion. They hold heat, raising local valve temperatures. They absorb fuel vapor, disrupting the precise fuel metering that direct injection relies on. The cumulative effect: reduced power, reduced fuel economy, rough idle, and in severe cases misfires and check engine lights. The temperature connection. Here is the critical insight that makes the $0 trick work. Carbon deposits begin burning off at approximately 1,400 to 1,600 degrees Fahrenheit. Under normal city driving conditions, intake valve temperatures stay well below this threshold. Deposits accumulate, but never reach the temperature needed to burn off. Under specific high load, high RPM driving conditions, combustion temperatures rise significantly. Valve temperatures approach or exceed the carbon burn-off threshold. Existing light deposits begin oxidizing and combusting. Japanese high-mileage drivers figured this out empirically decades ago. The $0 trick is built entirely on this combustion temperature relationship. The $0 trick: high RPM highway pulls. Here it is. Once every 1,000 to 1,500 miles, find a safe, legal stretch of highway and perform 3 to 5 wide-open or near-wide-open throttle acceleration pulls from approximately 30 miles per hour to 70 miles per hour in a lower gear, allowing the engine to reach 4,500 to 5,500 revolutions per minute before lifting. 3 to 5 pulls, once every 1,000 to 1,500 miles. Free. Why high RPM? At 4,500 to 5,500 RPM, combustion events happen 37 to 46 times per second in each cylinder. The combustion chamber is in a near-continuous heat state. Valve temperatures rise significantly above normal cruise temperatures. Why wide-open throttle? At wide-open throttle, maximum air mass flows through the intake port past the intake valve at high velocity. The larger fuel charge required for full-load combustion produces higher peak temperatures, pushing valve temperatures toward the carbon burn-off range. Why multiple pulls? Carbon deposits have low thermal conductivity. Heat takes time to penetrate into the deposit layer. Multiple successive pulls allow heat to soak progressively deeper into existing deposits, burning from the surface inward. 3 to 5 pulls in sequence produces substantially more deposit removal than the same pulls spread over separate drives. The science behind why it works. Combustion temperature versus RPM. At 2,000 RPM highway cruise, peak cylinder temperature is approximately 2,000 to 2,200 degrees Fahrenheit. The brief duration of each combustion event and the cooling effect of fresh intake air keeps average valve temperature well below carbon burn-off threshold. At 4,500 to 5,000 revolutions per minute under full throttle, peak cylinder temperature rises to approximately 2,400 to 2,600 degrees Fahrenheit. More critically, the rate of heat input per unit time is dramatically higher. The valve cannot shed heat as fast as it's being generated. At sustained high RPM full throttle operation, intake valve temperatures on FB and FA series aluminum heads can reach 800 to 900 degrees Fahrenheit. Carbon oxidation begins at approximately 750 to 850 degrees Fahrenheit in the presence of oxygen. The math works. The oxygen factor. Carbon oxidation requires both temperature and oxygen. During the intake stroke, the valve is open and fresh air flows past the valve face at high velocity. This fresh air provides the oxygen needed for surface oxidation of the carbon layer. High surface temperature from the combustion side plus oxygen availability from the fresh air charge creates exactly the right conditions for carbon removal. Before we continue, the $0 trick works best as part of a complete carbon prevention strategy. I've documented the full approach, fuel treatments, oil intervals, PCV maintenance, and this technique combined in the 500,000 mile car maintenance blueprint, link in the description. How to do it correctly. When to do it. Every 1,000 to 1,500 miles. Many owners tie it to every other fill-up as a reminder. Always on a fully warmed engine. The engine must be at full operating temperature before performing pulls. Cold or partially warmed pulls don't achieve adequate combustion temperatures. How to perform the pulls. Find a highway on-ramp, passing zone, or any stretch of road where brief hard acceleration is safe and legal in your location. On CVT Subarus, engage manual mode using paddle shifters or the manual shifter gate. Select a gear that puts you at approximately 3,000 revolutions per minute at 30 miles per hour, typically third or fourth equivalent. On manual transmission. Subarus. Select third gear. From approximately 30 miles per hour, apply full or near full throttle. Allow the engine to rev to 4,500 to 5,500 revolutions per minute. Do not rev past red line. The goal is sustained high RPM operation, not maximum RPM spikes. At 5,500 RPM or 70 miles per hour, whichever comes first, lift throttle and return to cruise speed. Wait 30 seconds between pulls. Perform 3 to 5 pulls in sequence. After the pulls, on turbocharged models, WRX, Ascent, Turbo Outback, Turbo Legacy, allow at least 60 seconds of idle before shutting down. The turbocharger has been working hard and needs continued oil flow to cool its bearings. This is non-negotiable on forced induction models. What you might notice: some owners report a brief period of slightly rough idle or slightly increased oil vapor smell from the exhaust for 10 to 15 minutes after the first few sessions on an engine with established buildup. This is normal and indicates the technique is working. Loosened surface deposits are being combusted and expelled through the exhaust. Frequency and realistic expectations. What this technique accomplishes prevents light surface deposits from accumulating into hard, thick deposits, burns off early-stage deposits before they solidify and bond tightly to valve surfaces, maintains combustion efficiency by keeping deposit thickness minimal, extends the interval between professional walnut blasting services significantly. What it doesn't accomplish: it does not remove heavy, thick, hardened deposits that have been accumulating for 50,000 or more miles without any cleaning. These deposits have solidified beyond what combustion temperatures alone can address. It does not eliminate the need for professional cleaning on high-mileage direct injection engines. It delays and reduces the frequency of that need. Realistic interval extension. FB25 with no carbon prevention. Professional cleaning needed at 40,000 to 60,000 miles. FB25 with consistent $0 technique plus supporting measures. Cleaning interval extends to 80,000 to 120,000 miles. That extension saves $600 to $1,200 per avoided cleaning cycle. The supporting measures that multiply the effect. Top-tier fuel. Exclusively. Higher detergent content in top-tier certified fuel reduces combustion chamber deposits that contribute to carbon accumulation. Cost 2 to 5 cents per gallon more. Essentially free, relative to the benefit. Direct injection fuel system cleaner. Every 5,000 miles, add a full bottle of BG44K, Chevron Techron Concentrate Plus, or Liquimoly Jectron to a near-empty tank before filling. These products clean fuel injector tips and combustion chamber surfaces, reducing deposit formation that contributes to carbon accumulation. Cost $10 to $20 per treatment. PCV system maintenance. A clean, functional PCV system passes minimal oil vapor into the intake system, which is the primary source of carbon deposits on the valves. Servicing the air oil separator filter at 30,000-mile intervals dramatically reduces the oil vapor load reaching the intake valves, slowing accumulation between cleaning sessions. Cost $15 to $45 every 30,000 miles. Half-interval oil changes. Fresh oil produces less vapor than degraded oil. Oil that's been in service for 6,000 miles has oxidized partially and produces more blow-by vapor than fresh oil at 3,000 miles. By changing oil at half the recommended interval, you reduce the oil vapor degradation that increases deposit formation rate. Occasional intake solvent treatment. Every 20,000 to 30,000 miles, some professional technicians recommend introducing a small amount of seafoam motor treatment through the intake vacuum line while the engine is at operating temperature. The product vaporizes in the intake manifold and passes over the intake valve faces in vapor form, providing mild solvent action directly on the valve surface. This is a gentle complement to the high RPM technique, not a replacement. The two together address carbon accumulation from multiple angles simultaneously. Cost $8 to $12 per treatment. Model-specific notes. Naturally aspirated FB25 and FB20. These engines accumulate carbon faster than average due to the FB25's known oil consumption tendency from low-tension rings, passing more oil vapor to the PCV system. The $0 technique is particularly valuable here. Apply every 1,000 miles rather than 1,500 miles if your FB25 has any measurable oil consumption. FA20D ITWRX turbocharged engines produce substantially more blow-by under boost, loading the air oil separator faster and delivering more oil vapor to the intake system. Carbon accumulation rate is higher than naturally aspirated engines. Apply the technique every 1,000 miles. Keep separator filter on a 25,000-mile replacement interval. Remember the mandatory turbo cool-down after each session. FA24DIT Ascent Turbo Outback Legacy XT. Same guidance as FA20DIT. Higher blow-by from turbo operation. Requires a more aggressive prevention schedule. EJ25 Older models. Port injected in most configurations. Intake valve carbon problem is dramatically less severe because fuel washes the valves continuously. The $0 technique still benefits EJ25 combustion chamber cleanliness, but urgency is much lower. When professional cleaning is still necessary. Signs that professional walnut blasting has become necessary despite consistent technique use. Rough idle that persists despite fresh plugs, clean throttle body, and functional PCV system. Measurable power loss compared to when the vehicle was new. Check engine light with codes P0300 through P0304. Misfires on an engine with confirmed healthy plugs and coils. Fuel economy decline of more than 10 to 15% from early life baseline with no other identified cause. Bore scope inspection showing heavy deposit coverage visible through the intake port or spark plug hole. At these thresholds, professional walnut blasting is the appropriate solution. The $0 technique then resumes afterward as the prevention strategy going forward. The bottom line. There is a $0 trick that removes carbon buildup from Subaru engines and costs absolutely nothing to implement. Perform 3 to 5 wide-open throttle highway pulls to 4,500 to 5,500 revolutions per minute every 1,000 to 1,500 miles on a fully warmed engine. Why it works. Sustained high RPM full throttle operation raises intake valve temperatures to 800 to 900 degrees Fahrenheit, sufficient to oxidize and combust carbon deposits before they accumulate into hard layers requiring professional removal. What it accomplishes extends walnut blasting intervals from 40,000 to 60,000 miles out to 80,000 to 120,000 miles, saving $600 to $1,200 per avoided cleaning cycle. Multiply its effectiveness with top-tier fuel at every fill-up direct injection cleaner every 5,000 miles, $10 to $20. PCV air oil separator service every 30,000 miles, $15 to $45. Half-interval oil changes for cleaner. PCV vapor. Occasional intake solvent treatment every 20,000 to 30,000 miles. What it doesn't replace. Professional walnut blasting when heavy deposits have already accumulated beyond what combustion temperatures can address. This is one of the simplest, highest impact, zero-cost maintenance practices available to any Subaru owner. Implement it starting with your next highway drive. And if you want the complete carbon prevention strategy documented alongside every other maintenance practice that keeps your Subaru's engine clean and running efficiently for 300,000 plus miles, check out the 500,000 mile car maintenance blueprint in the description. If you found this video helpful, be sure to watch this next video as we're sharing insider tips to help you cut repair costs and keep your car running like new.